check and see if you.
Yep. I just looked.
Okay, looks like everything is working at least. Maybe not done.
So
Okay, yeah, that works.
okay, and when I departed, I went to check that after the meeting I can access this records.
Okay, you should be able to, yeah, if you used your credentials. I just wanted to come and check.
Okay, yeah, thanks. Did you send the slides?
I did.
Can you do it now?
Yes.
Okay, well, thanks much for coming, and I don't know how everyone is doing, but when people were asking me about like, how am I doing, I was asking I'm having stress because of having no stress. So it's a little less pressure that makes you scared. Oh, please pass around those. So we will use an hour from 5 to from 5 to 6 for practice talk of Diane, who is giving job interview talk soon, and before that we will go over the skills that you all need for the research. So the research that we are doing deals with computing electron dynamics that occurs due to interaction between electronic and nuclear degrees of freedom, and it is not possible without computing non-adiabatic couplings. So this procedure needs to be covered, otherwise we cannot progress too far. So it will be about 3 meetings about this subject, how to compute couplings, how to run electron dynamics, and then another meeting on observables. And first meeting is kind of split, half today, half next time. So for another part about running electron dynamics, there is a sign-up list. So just judge what is your best skill, and we'll cover it later. And it's fine to have more than one name or sign for more than one subject. I'll clean it up. So there are no printouts of Dr. Mikhailov's talks, but there are printouts of other talks that we will do during the first hour. So if you are doing this activity for a long time, it will be not a big novelty and big surprise for you, but if you are joining, if your name is David or Kevin, please follow what is being presented carefully, take notes, ask the speaker, because it will be an activity for you to follow on the everyday basis. So please try to be brief. If no one asks questions, if things seem trivial, just keep rolling. And there will be 2D, not two-dimensional, but Daniel will do it. Daniel is and you won't, they will cover standard things, which are not super challenging but important, then you will cover the most essential part, but without bells and whistles, just the core of computing and numeric. And if there will be time before 5, then Aaron will tell how to project it towards spin-orbit coupling. If time is up, then Diane will start presenting. Yep, please start.
So subject I'm cover really briefly is how we compute heating and molecular dynamics. So basically, when we heat up a molecule, it requires the nucleus, nuclei, and all these forces interacting with each other. So here are the two equations, the top equations for the heating and the bottom equations for molecular dynamics. So this is just the NCAR for the heating. The important ones is the temperature that you begin at, the temperature that you end at. So this just relates on how you know your material would react to in real life situations. So yeah, if you put the final temperature up to about like 5,000, you should know that your material will probably combust. And so if you do see the molecular dynamics, you just see everything blow up. So this is just important how, if you want to control it, the temperature. The other thing that's also important is the NBLOCK. So what the NBLOCK does is when you introduce a heat to a material, it will cool off after a while, just like anything will in real life. But however many steps you put in it, it's gonna kick it back up to the initial heat or the final temperature that you want it at. So it's just gonna keep kicking it back to that initial temperature. And what that kind of looks like in a face off of a graph is just like this. So you see that the material is decreasing, and then since the NBLOCK was 4, it was kicked back up to the initial temperature. Then it cools off for a little bit. It just keeps doing that. Since the NBLOCK was at 4, you see that every 4th step it is reintroduced to be kicked up. So this is important because whenever you heat it up, the next step is molecular dynamics. So this is just an example of the NCAR for molecular dynamics. So if you haven't seen it before, you just need one of these. And then after that, using VMD, you can also see visually, upload it to YouTube, so you can use it for slides as we have been doing it previously. So yeah, if you follow these settings in VMD, you should be allowed. You can also see the output, so if you have a preferred output, you can. The only thing I wouldn't recommend is just the JPEG frames. Unless you've set it to a directory, it's just going to give you a bunch of pictures. Just make sure you don't put it like on your desktop or something, because it's just going to be spammed with images at every step. Yeah, is there any questions?
Okay, let's thank Daniel.
Can you explain what NBLOCK is again?
So changing that parameter, it just reintroduces the heat at what you want it to. So since in the previous slide you saw the NBLOCK was set at 4, so you see right there. I don't know if you can see it, but 4, it's kicked back up. The material's decreasing until the 4th time step. Then it's kicked back up to the temperature. Then it relaxes down to a stable point. Then at step number 8, it's reintroduced back up to the heat. Then you see step number 12 again, and that's what changing the NBLOCK does.
So it means that every 4 steps you reheat it back up again?
Yeah.
Okay.
Any other questions or comments? concerns.
How long should you repeat this healing if you have unlimited resources?
Well, if you put the NBLOCK at
Not in block, but NSW on your slides. Right?
oh, the number of cycles.
Mm-hmm.
If you have the well, I mean, you optimize the structure first, but I guess like I would say somewhere around less than 300. You want it that much?
Yeah, numerically yes, but is there a physical criterion based on this figure? Like, if you do it long enough, how this temperature versus time should look?
I think from what this is looking like, it's gotten stable right here. It looks like it's just repeating the same trend.
So it should converge to your desired temperature. It should stop dropping to zero.
Oh, so you're saying it's just gonna stay linear at the top?
It should, yes, it should converge.
Okay, I didn't know that.
More
Thank you.
questions to Daniel? If not, let's thank him again. There are no printouts for David's talk, but it's available online.
So I was looking at absorption spectra. And you need to make sure that you have a healthy wave card to make your absorption spectra, which in your in-car file means you need to have L wave equals true. Then after you run your job and VAS, you need to create a input overlap file and energy pop file. And I just have a very simple way of doing that right here, where you actually physically make the input overlap and then use a code to create the energy pop. And if you're doing spin-polarized, and it's slightly covered up here, but it's a slightly different code. And I actually, if you want copies of this, I do have a few copies of this I printed out.
What is on the right?
That's an example of the input overlap. So in this situation, I just picked a random molecule that we made during the class. It had 201 bands. So I have your starting band, your final band, and I'm not sure what the last one is for.
Nothing for.
Isn't it first band, homo, final band?
Just first and last.
Just first and last?
Yep.
And it doesn't necessarily have to be one in whatever the last band is. It's the first one you're looking at and the last one you're looking at.
Don't you need information about the homo lumen gap?
Here, no. If you...
You do, when you're making the absorption,
Yes.
you will need to look up what the band numbers are.
But the first number should be below homo and second above lumen. Otherwise it will generate garbage.
Okay, I guess we wrote our own equations for absorption. How is absorption calculated here? What?
Don't ask me, ask the speaker. And make sure that if he speaks long, then you have no time to.
Okay, never mind.
What should you do if your system has like 2,000 bands?
You're going to want to minimize the number that you're using. So you're going to want to do 100 or so above LUMO, 100 or so below LUMO.
Mm-hmm.
Or not below LUMO, below HOMO.
Mm-hmm.
Universal, how do you choose?
What?
How do you choose? How many orbitals do you include?
It's not an exam, you can say something you're not sure about. Just hypothesize.
All I know is you're looking for somewhere in the couple hundred range, but I'm not entirely sure where that
What
number
would
comes
happen
from.
to your absorption spectrum if you take too few of these orbitals?
It's not going to give you very...
So which range of spectrum will be hidden if you don't take enough orbitals?
high energy.
Okay. to dig deeper.
So,
So if you need higher excitation energies, you need to include more
Yeah.
orbitals.
Question. But the codes that we have tend to stop working if you have too many.
Exceedingly young.
There is way to
They're
running, but it will be slower and slower.
Yeah.
Okay. That's my.
Then at this point, you need to generate an OS strength file, and if you're working with in a no spin situation, there's the code, and it'll generate the file for you. And if you're working with Spin-Polarized, there's a couple different codes, and they'll generate unique OS strength files, which you then need to merge into a single file. So you're looking for ones that have transitions, and then merging those into a single file for you to work with.
So what, can you just cover it a little?
So what these two did is the same, give you the same information as this, except they do it, one of them does the information for the alpha orbitals, one of them for the beta electrons.
Okay.
And then what I did down here is I first went through and found all the ones that had a transition from occupied to unoccupied.
Oh, so this version of the code includes also transitions inside the band. And if you need absorption, you need to remove transitions inside the band and keep only transitions from occupied to unoccupied.
The way I understand it, yeah.
Very good.
It looked super close at the file when I was doing this.
Mhm.
And then what these last couple ones do is take the output from these and merge them into a new OS strength file, giving it the same form that you would have if you have a no spin file. That's not the way I remember making this. So then you're going to need to actually create the plot. You need to use this code, which yeah.
Can you interrupt? If you're not showing the content of oscillator strength file in the next couple of slides, can you just briefly tell what does it contain?
Apparently I didn't include that. I thought I had that.
But you can verbally address.
So it includes the transitions, the orbitals that are being transitioned, so the occupied to unoccupied that's transitioning. It includes the oscillator strength, which is a measure of how likely they are to transition. It includes the energy that would be involved, and it includes the
You want to say transition type?
yes, yes I do.
Does it partially satisfy curiosity of the end?
yes.
Okay. Okay, please keep going.
I thought I had that slide. I must have accidentally removed it when I added the spin-polarized content. So once you use this, you're going to get a couple of new files. And these files allow you to plot the absorption spectra. And you use this code, and there's a few different versions of the code that will give you different outputs. This code, for instance, will give you the output in EV. There's ones that give it to you in nanometers. And then this last section of code here converts the output of this to a PDF. And for some reason, my computer likes to turn things when I send it. Assuming you do it correctly, you end up with.
We can just lay on the site to spend.
you end up with absorption spectra, and you'll notice that I made one with EV and one with nanometers. And for Dan's question, I do have the formula for the absorption up there.
Where Fij is the oscillator strength between I and J.
Yeah.
Well, that's some smeared delta function. It's not. With this delta function, you just get lines. So you have some sum over, and so it's not really.
Yes, those functions represented by finite width. More slides?
No, that was it.
Okay, let's thank Dave. Let's check if there are questions.
Okay, is this the exact same thing we learned in class, or are there differences between what?
This is all but identical to what we learned in class. I took my PowerPoint that I did for class and added a few things to it.
Okay.
More questions? If not, let's thank David once again. So the next will be by Yolanda, and the next talk is a mini talk. It contains only 5 slides, but they are critically essential. So if the speaker will try to present them quick, you may try to stop or ask questions. So it is most essential part in the practical skills for the group for the whole year. And we are not doing this meeting, series of meetings for developing or proving equations, but the idea is that the orthogonality of electronic states is maintained if geometry is steady, but if the nuclei are subject to change of interatomic positions, either elongation, contraction, as Diane, Nathan, and all other members of Professor Krzyzewski group doing, will be subject to break of orthogonality relation. And if the positions of atoms are shifted due to molecular dynamics, it also will be a reason for orthogonality between Kohn-Sham orbitals is not maintained. And the practical steps needed to quantify this effect will be presented by Yvonne.
So suppose you have already completed the MD calculations. So if you want to get the energy fluctuation, you need this script. So this script needs 2 arguments. So this is just an orbital interval. This is the starting orbital. This is the final orbital. And you just follow these steps and you will get this kind of a figure. So this figure shows the evolution of Kohn-Sham orbital energy as a function of time. Because since my duration of trajectory is 1,000 seconds, so here we can see 1,000 femtoseconds. This is energy.
How would this image look if the temperature is 0?
There is no fluctuation.
So the increase of temperature would be resulted in larger amplitude of these fluctuations.
Right.
How should we interpret if there is something like this looks like quasi-periodic, but if suddenly one orbital energy goes from one band to another one, or there is something dramatically changing, how to interpret it?
There's some band crossing.
Or some reactions. So if the system is far from equilibrium.
Mm-hmm. So we may want to extract intermediates from molecular dynamic trajectory, and we can use this kind of code. So there is one point we should pay attention, because this code is based on VASP4. So if you are using VASP5, then you need to modify the postcard. So this is a postcard file from VASP5. So we need to delete this additional line. After we do that, we can successfully run this code. So if successful, then some files like P000, P999 will pop up. And this file corresponding to geometry of intermediates. Questions?
I definitely have a question, but I do not know how to formulate it. DM may have questions.
What question might I have?
What are these P000 files?
What are these P000 files?
It's just snapshots along MD trajectory.
And what is the format of these files?
It's basically like the postcard.
So
Also, their coordinates.
yes, and they are in the VASP format. There will be, after running this command, there will be 1,000 postcard files, each of which corresponds to one subsequent step along the molecular dynamics trajectory.
And for each of those postcards, you have to calculate the energy.
Later on, yes. Yes.
At this stage, this file just corresponding to atomic position.
So you calculate them all at the same time?
No,
They
no,
don't
one
depend-
runs molecular dynamics, which is a standard task for VASP. And then with the script, one extracts the trajectory which is hidden in the out car and XDAT card into so many individual files.
And they're all saved. Yeah.
They are saved in the directory where you run this script.
The outcome. Or reach the outcome.
Originally, they're saved in the out car, but this it's kind of unzipping from one file into 1,000 files or whatever how long your dynamics is.
Okay, then another script takes two at a time and performs single point energy calculation?
Yes, and it will be covered in the next slide. But this is could be interesting for a group of Professor Krzyzewski because it is a replacement of what you do in your normal modes when you shift positions
Mhm.
of each ion to the left, to the right, one by one. And in some
Yes.
sense, you also have set of different geometries for which you compute the electronic structures and then use it for couplings. Here, these shifts are not by moving individual atom in a organized way, but it is a simultaneous motion of all atoms along the trajectory. But it serves the same role as in your approach shifts of individual atoms. Make sense?
Yes.
So next step is to calculate non-adiabatic couplings. So these are necessary files for the coupling calculations. Basically, we need 10 files. So the income. So here is the format of input overlap. This is the starting orbital, final orbital. So typically, I just choose maybe 160 orbitals. It's 80 orbitals below HOMO, 80 orbitals above LUMA. And key points protocol, this is just a standard MD calculations. So we need a special income coupling. It is stored in this location. And also we need this 1,000 files from MD trajectory. We also need some script files. So we need a Corey script. This is a standard for running any calculations in us. Also, we need a bit script file. Here is what it looks like. And we also need some exe file. So for this one, we just extract some orbital energy, like energy bar. This one calculate oscillator strength. This is overlap between snapshots at adjacent trajectories. And this is the location of the exe file, and this is the location for the sh file. So after you have prepared all files, you can just submit your job with this command.
So it is what Diane was asking about. The script inspects the P00, P001 files with coordinates one by one. So there is a 1, 2, 3, 4, 5, 6, 7th line in the script that runs over this, time steps, and in each of them it runs VASP, and then it does extract the orbitals and compares orbitals at the previous step and current step. Okay. So, what is the output? What does one get in the directory upon completion of this job?
Some coupling files will pop up.
So, what is the what are the names and what are the contents of these files?
Yes, it's coupling dot some number.
So it's same format as for this positions, like for P000, it will be corresponding coupling 000. So as many coordinates, as many couplings.
Different by one.
One less.
Yeah,
Okay, and what is inside these couplings files?
it's just a transition probability.
But how is it numerically organized?
It's in a matrix format.
So it's a square matrix, and what are the indices of the square matrix?
It depends on your output. Depends on the input overlap. For here, it's 162, so it's 162 by 162.
So indices for this matrix are indices of orbitals involved.
Mm-hmm.
So it transitions from one to another orbital.
Mm-hmm.
So it generates 1,000 square matrices.
Right.
Thank you. And it's time for questions.
Okay.
Please.
562 is all orbitals?
No. It's
Just-
just 80 orbitals about Luma.
So 562 minus 401. And that's like your orbital, the number.
401 is LUMO? 401 is LUMO?
401 is
No.
401 would be like
401
normal minus 70.
401 is the number of occupied?
no, 401 is HOMO minus 80. So HOMO is
Lowest orbital
181.
is the meaning of this input overlap in Yulun's talk
Okay.
is the same as meaning of input overlap in David's talk. So window of orbitals involved in the calculation.
Okay, so HOMO is somewhere between 401 and 562.
Exactly. Yes.
What is one? But you don't know,
It's a heritage. It's vestigial.
but you don't know which one is HOMO and it doesn't matter?
You do know when you prepare this input.
But not from input overlap.
Hmm?
But not from input overlap, you don't know which one.
You don't record it. The input overlap doesn't need this information. because later on, partial information about which is occupied, which is unoccupied is stored in the occupation. Especially if the system was good. More questions to you?
Dan, how long is your talk?
Depends.
So
When you were practicing it in the bathroom?
I was.
Okay.
This is my practice.
How many slides?
33.
Okay. More
So
questions to
how does this approach scale with the number of atoms? What's the latest on the same question we have?
Let me translate your question. Will this method be substantially slower if you double number of atoms?
Well, I like my version fine. Or triple, quadruple.
Yes, probably because previously I was doing some calculation for 200 atoms, and the complete calculation maybe several weeks. And
Several
yes,
weeks. It's
Yeah.
like from this fence and until March. Okay, what my question is, I'm trying to compare the two approaches. The first is when I compute the normal modes and so on and so forth. So I know it takes 6n, where n is number of atoms of energy calculations by DFT software. And then I know the response of my system to small displacements of atomic coordinates. So how many steps do you need here as a function of number of atoms to compute your thermal averages?
I understand what she's talking about. I'll translate.
Okay.
So, if one is doing normal modes calculations or molecular dynamics, the time used to compute single point will increase with size of the system in both situations. But for normal modes, the number of single point calculations will be increasing with size of the system. Like if you go from 100 atoms to 200 atoms, it will be like proportional increase of number of steps, 6 and whatever.
600 to 1200.
Is there, in this approach, is there a necessity to increase number of single steps? Is there a necessity to increase the length of trajectory if one takes larger system?
what's the meaning of trajectory here?
Should one use like 2,000 steps instead of 1,000? Would it give any benefit for bigger system or?
I guess for the following calculations for non-radiative rays, there will be some difference. But if you are looking for some qualitative trends like emission, they are basically the same.
So no matter how big your system is, the length of trajectory can be kept in certain limits.
It's problematic, isn't it? I mean, if you want to simulate the chaotic thermal motion of your system, you need to move, ideally, each atom multiple times, right?
We can continue the argumentation, but the practical convergence is achieved very quickly.
What's that practical conversion?
The results, depending on the length of trajectory, starts converging if the trajectory is longer than 320 seconds to less than every bar.
So see, no matter how big system is.
Yes. Okay, but thank you once again. assigned to present today.
Wait, Dijon is not there.
I can wait until next week.
We'll never leave.
Okay, then we'll have next week more intense. Diane, do you want to present right away?
Yeah, do you want to, I send you the presentation, do you want to put it up there or do you want to hook up my computer? Which one will be easier?
Let's put your presentation. Can you please resend it? To,
Wasn't found. So you don't have in just your email anymore?
let's send it together.
You okay now?
Okay, let's move forward.
I'm all right. Tired. Seriously, are you like, looking for positions?
Well,
I don't
so
mean to twist the knife.
no. So there's a couple of papers that I'm working on. I mean, I haven't really been working on them much lately, but I'm cracking on that again here. So I'm doing that, doing carpentry in the meantime.
Carpentry.
Yeah.
Oh, Jesus Christ.
What's it?
Okay, let's do it on stick.
For real?
Yeah.
Are you well?
Yeah. Yeah. You got everything you need done. Because I know the guy to contact. He's a general contractor, so like you need electrical plumbing, like whatever. I mean, he knows people to contact for that. Make sure the job's done right.
Kevin and David, if you have more questions to Win after listening and reading the slides, feel free to just keep it around because it's most of the important part of the decision.
All right.
Hit F11.
Kind of puts it full screen.
Oh. How do I go back?
Oh, you can't go back.
Can't go back. Oh, I can't. Thank you for coming to my practice for my talk that I'm supposed to give on Thursday at my job interview. Today I'm going to be talking about some aspects of excited state dynamics in semiconductor nanostructures from many body perturbation theory based on density functional theory simulation results. This has been for the past few years the focus of my PhD work at North Dakota State University. I'm gonna begin with a quick motivation for our work.
I'm just wondering, like, what you do? Like, what's the audience?
And then I'm gonna introduce some of the excited state properties that we are interested in.
Okay.
Objectives and methods that we have developed. I'm going to introduce some of the nanostructures that we did work on, and those are mainly single-wall carbon nanotubes, pristine and functionalized. Then I'm going to move on to theoretical methods and approximations. gonna explain the different aspects of excited state dynamics that we worked on, and those are mainly multiple exciton generation, singlet fission, and today I'm going to focus on our latest work, which is exciton-exciton interactions in the final bi-exciton state. I'm going to finish up with some conclusions and outlook for future work. So our motivation is, how does I get this to disappear? Ah. Okay. There it is. Okay, so our main goal ultimately is to increase the photon to electron conversion in photovoltaic devices. No, this doesn't.
I'm going to hire you like this.
No, this is. Okay, so I'm not very.
Can you just download it to the desktop quick and open it up with like Adobe or something?
Keep talking about something.
Yeah, that was a story.
Better?
Presentation.
I think if you hit F5, it'll just go to full screen.
F5.
Oh, no.
Control L.
Can I just hook up my computer?
You can try to.
If there's a kind of presentation mode for this. There's nothing.
Wait, you want to make it a full screen?
Yeah.
Try hitting the arrow on the right-hand side. Will that help?
Arrow on the right hand side. This?
Oh, right there.
Yeah, that one.
No. Let's just hit some.
Try going on the View tab.
Read mode.
Yeah,
Full
try.
screen. There's full screen mode, but it's for some reason disabled.
I'll try read mode, I guess.
I tried that.
Oh.
It's cutting off. Has anyone hooked up an Apple computer on here before? What's the best
Oh shit, I don't have
version?
that.
Try to keep trying this.
I guess have a flash drive that you can try to transfer it over with real quick. Or wait, that's not gonna help anything. Yeah, never mind.
I don't know, I'm out of options. What was the...
I mean, read mode on Adobe should at least be tolerable. I think you just gotta use like left and right to click it forward and back.
Okay, how about this? It's just... We'll
That's
just...
good.
Yeah, okay. This looks like it works, only we have to see the tabs, but... Okay, where were we? Okay, so efficiency of nanomaterial based solar cells can be enhanced via carrier multiplication, or as I'm going to refer to it in this talk, multiple exciton generation. And this is one of the main methods to increase the efficiency of solar devices beyond the theoretical limit. In nanoparticles, MEG is enhanced due to the strong confinement. But the MEG process depends on competition with other relaxation channels, such as direct Auger recombination and phonon relaxation. So those all need to be taken into account. In chiral single wall carbon nanotubes, MEG is very prominent, and one reason for that is the small electronic gap, and also the strong excitonic effects that are exhibited in carbon nanotubes.
And the excitonic effect so strong.
Excitonic effects are generally strong in one-dimensional or quasi-one-dimensional systems, because screening effects are suppressed. Recent experimental work on lead selenide quantum dots in this case has shown that MEG could indeed lead to efficiency in nanomaterial-based devices of over 100%. Okay, so let's talk about excited state processes that we are interested in modeling in order to correctly predict the effects of MEG and uh, in the nanostructures of interest. So let's say we have a high energy excitation. High energy photon excites from the, this is dusting. Okay. A high energy photon excites a particle from, let's say, the valence band high up into the conduction band. And this is a high energy photon that carries energy more than twice the gap. The subsequent process that can occur is either carrier multiplication, where this extra energy that this electron possesses is used to create another electron hole pair or another exciton or another charge carrier, which is a favorable process in photovoltaic devices because it increases the current. So this is what I'm going to refer to as MEG. They two excitons from one highly energetic photon. Another process that needs to be taken into account is phonon-mediated relaxation. And this is the process of the extra energetic electron and hole losing their energy to atomic vibrations or phonons. They emit phonons and they relax to the band edge. This is an unfavorable process because you lose the extra energy. All you do is heat up the system. So we need a comprehensive study for MEG, MEG recombination, phonon-mediated relaxation, energy transfer, and so on and so forth. Those are all other processes that I'm not going to cover today. Today I'm going to mostly focus on MEG. And we're going to use density functional theory in combination with many-body perturbation theory in order to study MEG. We're going to look at carbon nanotubes as systems of interest, and we're going to study the effects of chirality, confinement, and also surface functionalization. We obtain our CHEM energies and energies, CHEM orbitals and energies using FAST software with the hybrid HSE06 functional as a temporary substitute for GW, and later, as we'll see, we check whether that is a good approximation. We use several unit cells from our nanotubes that we put in the same simulation cell. So we have a large simulation cell, so we avoid sampling the Brillouin zone, and we do calculations at gamma point only. The main contribution to the main part of my work is including the Peter equation and the MEG rates calculation in order to include excitonic effect. So what are my objectives? I want to calculate
Work for real, Dan. Objectives of my thesis work. That should not be in a job talk.
It's not there.
There.
My objectives are calculating the rates of exciton to biexciton and also the inverse process of a biexciton recombining into a single exciton. Then I will study the process of singlet fission, where one singlet exciton decays into two triplet excitons. Not one, two, will be remedied later. And then I'll move on to calculating bi-exciton self-energy, where we investigate the importance of exciton-exciton interactions in the final bi-exciton state. These are the systems of interest. These are the systems that I've looked at. Three different chiral carbon nanotubes, 6,2, 6,5, and 10,5. And this is functionalized carbon nanotube where two chlorine atoms have been attached to the surface. So we'll study the effects of functionalization. We use density functional theory to obtain our single particle energies, if you, or our Kohn-Sham. We use the Kohn-Sham orbitals from density functional theory and Kohn-Sham energies as a basis in which we perform many body perturbation theory calculations. It's so our Kohn-Sham states are essentially effective fermionic degrees of freedom. And this has been a standard approach to many body perturbation theory calculations in a certain basis recently. So this is a major simplification because the explicit and electron wave function is not needed. Throw that stuff away. This is our.
I'm sorry. Major simplification is that you extract the observables from correlation functions. Not that you're using Kohn-Sham bases. If you will find somebody in the audience who knows many body quantum mechanics.
Right, if you have the n-body electron wave function, then you don't need to. Right. So we begin with our microscopic Hamiltonian in terms of the field creation and annihilation operators. And we try to describe all the relevant physics that are involved here. This is our free electron term interaction with ions, the Coulomb interaction, and interaction with an electromagnetic field or with photons. Here we use the Coulomb gauge for our coupling between electrons and electromagnetic field.
Can you stay for few more seconds on the previous slide?
Yeah.
So your expression for current, if it doesn't include gradient.
It does include gradient.
How this gradient will look in the momentum space, and how this equation will look if you try to program it based on output of last one.
My next slide will partly answer that question.
And can you point equation which we are discussing?
Yes. We're discussing this equation.
Dan, while you are interrupted, strictly speaking, this is not complete expression for the current. There is also a term that is proportional to field A, right? You aware of that?
Yes, it is.
Well, add dot 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 or something, or at least say that this is only with paramagnetic piece of the current operator.
Um, then we cast our microscopic Hamiltonian into the CHEM basis, and we change basis from the electron field operator to CHEM orbitals and annihilation and creation operators. So our Hamiltonian takes the following form. So in perturbation theory, we treat all the possible interactions as perturbation to the free Hamiltonian, to the non-interacting. So when you, to answer the question, this is what the current looks like in the basis of CHEM orbitals. And when you convert it into momentum space, was your question, to what happens to the gradient? It becomes just k, just momentum. It turns into just the value of momentum. Does that answer your question?
Mm-hmm. And if you remove summation in the expression for current, it will be partial contributions between each pair of orbitals.
Yes, if you remove the summation over ing of the
everything under summation, then it will be partial contribution from each pair of orbitals.
That's right.
Why you ask?
For pedagogical reasons. So the expression that, can you point with your green light here? So this thing there, it is transition dipoles that are stored in the oscillator strengths file, which are used to compute oscillator strengths.
Only the thing in the brackets. This
Yes.
creation and annihilation operator terms are needed to do many body perturbation here.
Yes. And since orbitals are stored in the momentum space and in the last place, gradient is replaced by just value of momentum. If one looks inside the code for oscillator strengths.
Okay. We have a piece in our Hamiltonian for the two-body Coulomb interaction between CHEM orbitals, and this piece just needs to be subtracted in order to avoid double counting the electron-electron interaction that has already been taken into account by this CHEM potential during DFT calculations.
What was your alpha? Is that just a spin?
Yes.
Variable?
Yes, alpha is a spin variable. Yes. Yes, this is the ith CHEM annihilation operator with spin alpha.
Then you sum over those two.
No, depends on what you want to study.
Does your Hamiltonian
Wait,
depend on spin?
In this, yes,
no,
this is
it's
spin
sum
and
of
alpha and beta here are stand for spin. Any
Your Hamiltonian does not depend on spin, right? So there better be summed over.
Oh.
That's all there is to it.
Okay. It includes spin. So in order to include excitonic effects, we need to take into account the Coulomb interactions between particles and holes. In order to do that, we calculate corrections to the bare particle-hole propagator. One way to do that is to calculate the Coulomb interaction. One way to do that, I've practiced how I introduce this slide. I have.
Just tell what is the meaning of line.
Tell us the story.
One way to, so in order to introduce excitonic effects, we need to calculate in order to introduce excitonic effects in with perturbative techniques, we need to include the Coulomb interaction between electrons and holes to as many orders as we can.
Diane?
Yeah.
Would it be right or wrong to say that number of vertical lines in your diagram agrees with the order of your correction? Like one line,
Yes.
one
Yes.
correction, two lines, two corrections.
Okay. I keep forgetting. I gotta make this talk more for more
General audience.
less check. Okay. What's my time? 5:15.
Well, don't worry about time. I think it's more important at this stage
I
just
want to go.
deliver your message, right, and find a way how you. Suppose something happens during your presentation. People might interrupt you, some technical issues. Just talk. This is your talk. You are a master here. Don't worry about time or anything. Just explain.
General background.
The physicist.
Okay. The way we include excitonic effects is we start with the bare electron hole propagator and we dress it with by adding the Coulomb interaction between the electron and the hole to infinitely many orders. And we make the ansatz that if the Coulomb interaction is added to all orders, then we obtain an electron hole bound state. And this electron
result.
But don't interrupt.
Okay, I'm sorry, ma'am.
This
Let me
electron
finish, then
hole,
you will tell.
this electron hole bound state is presumed to include the Coulomb interaction to all orders. So this introduces extra pieces in our Hamiltonian, one that describes the electron exciton coupling and one that describes free excitons. From this piece in our Hamiltonian, we can obtain what's known as the Bethe-Salpeter equation, which is a standard approach in treating excitonic effects. And the way that the better. So Peter equation is derived as you start with the electron exciton coupling term, which already includes all Coulomb interactions by definition, and you add one more Coulomb interaction, which means that you're changing nothing to it because they're all already included. And there are two ways that this can be done. So one obtains two terms on the right-hand side of this equation. One is known as the Coulomb term, the other one is known as the direct term. And the direct term includes all the screening. The Coulomb term, as you all probably know, is not screened. And this is these are the expressions for the Coulomb term and the direct term in terms of Kohn-Sham orbitals. So these rho EHs here, which we refer to as transitional densities, are constructed from Kohn-Sham orbitals from density function node theory alpha.
Can you stay for a few seconds? So why do you have k squared in the denominator?
Because in momentum space, the Coulomb interaction goes like 1 over k squared.
So Fourier transform.
Fourier transform
One over
from
R.
position space into momentum space, one obtains 1 over k, one obtains k squared in the denominator.
And I probably missed, because I came a little bit later, but why actually you need to represent this in a k space? It's more natural probably to put it in an x space, xyz space, in coordinate space.
Well, we use periodic boundary conditions for our calculations, and so we solve our Kohn-Sham equations in VASP, which are solved in k space. So we take our Kohn-Sham orbitals in k space from VASP, and we don't bother Fourier transforming it back into position space and
So
doing
this is
everything
just
in
because
position space.
this is just because of the software which you use. There are no any benefits of doing this.
You just want to save time on Fourier transforms.
We want to save time on Fourier transforms, and I believe our calculations, our expressions are easier to calculate in k space than in position space.
See, you have this k equals 0 is excluded, right?
Yes.
It's easier to do in the k space.
Why is it easier? How does it deal with k zeros? So what?
It is a very long story.
But it's very
Yes.
well. I mean, it's a possible question, right?
Okay.
People might ask, like, do you have any reason for using k except just software? And if you really believe that this is something
I believe that our
that
expression.
this is technically important, right? I'm not sure about conceptually, but technically important. Then again,
Well, if it's phi of x, how would you exclude k equals 0 mode?
but if I put in xyz, why there would be k mode? Everything will be in x space.
But well, it so happens that you need to exclude k equals 0 mode. And it's much easier to do if everything is in k space. That's one reason, aside from that, WASP spits it out in k space.
But if I will have software calculating in plane waves, not in plane waves, but in a local basis, then everything can be done in xyz. Then there is no story about k naught.
In principle, yes, but you need to worry additionally about excluding k equals 0 mode. So k equals 0 mode is space average, right? Integral over space. You told not to interrupt. Right? You interrupt.
No, but he finished.
No.
He finished this slide at least.
Yes, yes,
Oh,
like
at
that.
least this, like,
Yeah, and haven't thought about it other than we use fast, but everything is in case based. So I don't
you know,
know how.
people you're going to, they know about FFT and such. You know, for them, that's no reason. Position space, case space, you know, split second from one to another, FFT.
But it takes time if you do really computations, right? So why to do extra effort on this?
Well, if you were doing things in position space, it would be extra effort if you use fast. As far as deriving the expressions in position space and seeing how much
Well,
easier everything
I think
will
you
be
also
then.
probably can then justify that it's not just because you write it for the software. You're probably interested in semiconducting nanostructures, right? And like one-dimensional, two-dimensional. So periodic boundary conditions are very
Yes.
effective tool to use there. So that's why the choice of the software is not just because we have VASP and nothing else, right?
Right.
It's
Mini
dictated
period
by the materials since you're interested, like
in carbon.
in one-dimensional, you can be broader than just nanotubes, right? But you're interested in the nanostructures, like one-dimensional, two-dimensional, low-dimensional nanostructure, something like that, right?
Yeah.
And again, because it's semiconductors with a crystalline structure, periodic boundary conditions is very efficient solution, and then getting to K-space is a natural thing to go.
Yes.
And that's actually why you choosing VASP as software, because it was specifically designed for the semiconducting materials, right?
Yes.
And that's why you deriving these tools in a K-space. If it would be for molecules, I doubt that VASP would be a good choice. Or actually, you will have any benefits to doing this procedure in a K-space, right?
So we're trying to do quantum dots and
So I think you need to think about not only, how to say, from the point of view of deriving methodology, but really you apply, like you're not just deriving the universal thing for everything, right, for the universe. You probably really design your software focused on a specific, like not one or two types of materials, but some class of materials, right?
Yes.
And
Yeah, I
don't
can
be
just-
shy to really highlight it,
Yes.
because then people understand that you understand not only kind of deriving things, but you understand the systems, the models which you are working on, right? That you're really an expert in this field.
Yeah. Or, yeah. Why we use VASP? I can justify. Yeah. And this is our full expression for exciton electron coupling when we have triplet excitons we'll be interested in singlet fission where singlet exciton decays into two triplet excitons. So we need a way to deal with the triplet excitons. One thing that is different in this extra term in the exciton, in the electron exciton coupling part of the Hamiltonian is these are now triplet exciton energies and triplet exciton wave functions. That we obtain by solving the Betzel-Peter equation for triplet excitons, which I will talk about later. But first, I'm going to talk about screening. So this is the screen Coulomb interaction that appears in the direct term of the Betzel-Peter equation. And in terms of our transitional densities, this is what the expression for usually referred to as polarization insertion. This is what it looks like in terms of Kohn-Sham energies and transitional densities. So this is evaluating this is relatively expensive for big systems, it becomes impractical. So we work in what's standard method, what's standard approximation is called a static approximation, where we compute this polarization matrix at omega equals 0. And for solving Betzel-Peter equation, this has been shown to be a valid approximation because of cancellations that appear in the screen-Coulomb interaction and the Green's function.
Yeah.
Yeah.
Can you say on a lay language how to interpret this polarization, like in the common sense? Polarization of solvent is static at 0 frequency when dipoles just rotate according to the electric field. And here your polarization is frequency dependent. So it means that how to interpret it? Like charge distribution oscillates in time and according to your source, or what's the physical picture behind this equation?
Yes, so technically one needs to calculate polarization at different frequencies. But when you solve Betzel-Peter, it is too expensive not too expensive, but well, it can be done, but it is much more difficult to solve the dynamical Betzel-Peter equation. So therefore, one has to make this static approximation for the screen-Coulomb interaction in order to solve the Betzel-Peter equation in the form that I showed it earlier. Otherwise, the Betzel-Peter equation takes a whole different form, and it's much more difficult to deal with. But this approximation has been shown to be valid because of cancellations that appear once you write it all out in terms of the in terms of full omega.
So since you have it on your slide, it says okay, static approximation okay for Betzel-Peter and not suitable for MEG. You know, either remove it or talk about it.
Yes, later for MEG rates, we will make an attempt to go beyond the static approximation. And that will be introduced.
So you suggest to not use it here, but use it later for the results, right?
I don't know. My rule is anything you put on your slides, either talk about it, be prepared to explain, or not put it at all.
It looks like it's more like a result, right? This is your observation that this approximation not very good for multi-exponent, right? Or this is what was known from the beginning.
Yes, from deriving the expressions, you can see that calculating MEG rates at omega equals 0 would not be. I haven't looked into detail, but when you derive the expressions for Betzel-Peter equation beyond the static approximation, then there it somehow becomes obvious that when you set omega equal to 0, it's not that much of a approximation because of cancellations that appear. I'm not prepared to talk about this in detail.
Then, if I may, a lot of people would disagree with that statement. So I suggest you just say, you know, it's kind of okay. A lot of people do static approximation for beta-salpeter. We do it for simplicity. Don't.
I'm confused. Your goal is to calculate MG, and now you're saying the static approximation doesn't work. It means that you don't really use it, right? Since it doesn't work. Then why are you really talking about it?
The static approximation is used for solving beta-salpeter,
Fine.
which is one step in our calculations.
Oh, okay, fine. Yeah,
which we
then-
need to do before we can calculate MEG rates. And in our calculations for
Then-
MEG rates, we
Perfect. Then
make an
instead
attempt.
of trying to make a contradiction between this and that, as
Mhm.
Andre already mentioned, that some people might really disagree or have different opinion, right? And you
Mhm.
don't want to really create a discussion on the middle of your presentation, right? Because then you probably, then everything will go on not under your control.
Yeah, that's
So
I try
So
to put-
probably just put your, really thinking that you really say, as our first step, we need to get the beta-salpeter to solve beta-salpeter equation. As a very common approximation, we use static approximation for this. However, our goal is go beyond just this, but go to the carrier multiplication. And for this, we need to do extra steps or extra whatever.
extra
something.
calculations.
Extra
for MEG.
calculations to really do MEG. So we need to go beyond the static approximation, right? That's it. Then there's no contradiction and people understand very clearly, oh, okay, he's doing this, he's doing that, fine.
I see. So at this point, it's hard to tell whether beta-salpeter and MEG are separate calculation, and you
Yeah, you put it as a contradiction. Like this works for this, but doesn't work for this. But instead of this,
I
if
see.
you use it as an intermediate step to get your final destiny,
Oh.
put it as step 1, step 2, or something like this.
Again, I recognize all of this. I mean, then instead of, so okay, approximations to screening. So this is what we would like to evaluate, but it's technically very challenging. So first thing we do static approximation.
Mhm.
The reason I wrote this, so it turns out to be okay for beta-salpeter, but not so good for MEG. We will try to rectify that. Next approximation, inversion of the metrics. And then
But with beta-salpeter approximation, you already can get some physical observables, such as absorption spectra, for example, right? So it's not just it's good for this equation. You can get valuable observables which can be compared to compared to the experimental results or something. So you can also mention.
So again, and be aware that there is community that believe that even for beta-salpeter, static approximation is not very good. It's very difficult to go beyond static approximation for beta-salpeter.
So would it be accurate to say that, you just basically leave everything as is, but instead of saying okay for beta-salpeter and not suitable for MEG rates, could you just say okay, or used for beta-salpeter, not used for MEG? I mean,
To
would
go
that be
beyond
kind of
what-
would that be an
Not-
accurate way to
not
sort of
as-
sidestep the whole confusion, I guess?
Most part also use static approximation for MEG as well, because
Okay.
it's technically very challenging.
Yeah.
But don't you do dynamical approximation for your?
But like, you just
Yeah,
come right
for
out and say
one-
you use it for
Dynamic-
this, not
For
for
one
this.
system, well, for two systems.
But I thought that this is your main, that's why I'm saying, it sounds like it's a main conclusion from when you're applying this to different systems, majority of systems shows not very good agreement with experiment if you stay with the static approximation for MEG.
It's only one system.
And that's why you have to go beyond it. And you have done one system, but technically you can do probably more than one.
Why, I can do many.
So yeah, on slide number
Wait.
12 and
From static.
from 33.
Yes, then you need to radically speed up, so.
We have 1 minute per slide. 'Cause otherwise-
Another approximation that we make is what we refer to as the uniform medium approximation, which is where we set k equals, or set p equals to negative k, or in other words, we retain only the diagonal matrix, the diagonal elements of our polarization matrix. So this would be valid for uniform systems where the Coulomb interaction depends on the difference on the distance between x and x prime. So carbon nanotubes, pristine carbon nanotubes are more or less uniform systems, so this would be okay for at least carbon nanotubes.
So it's a hard sell. I mean, it's not a uniform system. Again,
It's
in one dimension it's more or less
yes,
in
yes.
two other it's not. It just happens that, for example, if you compute absorption, then you reproduce E11 and E22.
So with this approximation, we compute absorption and we reproduce E11 and E22 with relatively high degree of precision. So this is comparison to experimental data. And for our tree system, we see a very small, about 13% deviation from reported experimental results.
So sorry, it's while you're on this slide, just so germane. So Braden, it seems, has recomputed E11s for 6,2 at least, beyond the in a K, P approximation. I just looked at his results. What he's seen for E11 is, for example, is 1.22, which is much closer to Weissman-Bachila. Do you have his result at all? Did you discuss it with him?
I have my own results there. That sounds right. I also.
Why is it not there?
This is because all our calculations are in diagonal later that will follow, or by excitons, or I can add it to this, but
well, see, it's much more palatable if you, yes, if I work harder, I am that much closer to the experimental result. If I work less, yes, I am making a mistake, but I know that, I can improve it.
I can put that in. I can.
Why haven't you?
Well, later on, this is not what's used later. So this is a Feynman diagram for the MEG process. Here, one electron decays via the Coulomb interaction into an extra electron hole pair. So this Feynman diagram, which is in the independent particle Hall approximation, needs to be rectified in order to include excitons. So the way we do that is we trace every non-interacting particle Hall line that we see in this diagram with all possible all possible Coulomb interactions, or which is what we saw earlier is the way we incorporate excitonic effects. And if we do that to all orders, you end up with a diagram that looks something like this. Electron hole, an exciton wave function is coupled to an electron hole pair that interacts to Coulomb interaction with another electron hole pair. And the result is two excitons are created from one extra energetic exciton. So the next thing one needs to do is to find all Feynman diagrams that contribute to this process of one exciton to two excitons. So these are the two diagrams that we find. And we compute rates.
What's that vertical line in the middle? Is this part of a Feynman diagram? Or what is it?
The vertical line represents the final state of your rates of a single exciton to two excitons.
How's that? It's just a line that goes from up to down. What's the final state? Where's the final state?
The final state is everything that this line crosses. In this case, it's two excitons. So this is how rates are calculated. You find the Feynman diagram that you're interested in, and you cut it in half, and whatever you cut is in your final state.
Is it possible
In the
to
final
put,
expression, yeah.
time axis on this diagram?
It is,
Hmm?
yes. It
So
is.
we
There
will
are-
go from left to right or right to left?
It's left to right, usually. Everybody draws Feynman diagrams differently. I'm going for a less busy slide, hoping everyone knows how rates are calculated and what cutting it means. If you mean cutting a Feynman diagram means you're calculating rates. And wherever you cut, that's your final state. So different expressions come out depending on where you cut diagrams. So the expression that corresponds to cutting this diagram down the middle would correspond to a rate of one exciton to two excitons. So that can be a question I can answer if someone asks later what that line represents.
So this diagram, what is its contribution to? To which object?
To MEG, to which process you mean?
No. To which like object? What do you compute using all your Feynman diagrams and all that? Exciton
To which-
propagator, right?
Oh, okay, yes, exciton propagator.
And all the times inside, what about them? Are they pinned down? Are they fixed? So say you compute exciton propagator correlation function from like time 0 to time t, right? So those are pinned down, those are fixed.
Those are pinned down, yes.
What about the times in the middle?
Those are integrated over.
It's to the question of Professor Killian, which way time flew.
But yes, but still that's a valid question you can put. All right. Right. Yeah, the times inside are integrated over. They're totally arbitrary. How you put them.
What other indices do those lines carry, and what are those lines? So everybody's not so bored.
Which lines exactly are you referring to?
No, I was trying to stay awake. Well, you see these are pictures because they depict. They're very informative. They depict the actual processes, right? So
the thick lines represent excitons, and they're represented by these psi's, which carry indices I, J, and alpha, beta, or gamma, which alpha, beta, and gamma represent which exciton it is, and I and J label its particle hole content. The lines with arrows represent quantum orbitals, and the wavy line represent Coulomb interaction between electrons and holes. So these are our expressions for the rates that result from these calculations. You can recognize the Fermi-Golden rule structure um, of these expressions. They contain the screen Coulomb interaction evaluated on some representative omega, not which is not zero, but is carefully chosen. So that we can slightly improve on our static approximation, which we now go beyond in our MEG rate calculations. Does this answer?
Sorry to interrupt, but as Professor Killian said, if you had infinite resources, you would compute what? As far as dynamical screening is concerned, right?
As far as dynamical screening is concerned, you would compute this screen Coulomb interaction on omega gamma. This would be omega gamma in here. So rate depending on omega gamma. So for every omega gamma that, for every exciton, which this exciton is omega gamma. Is that evident from the expressions? Because there is energy or here, yes, energy conserving delta function. Omega gamma minus omega alpha minus omega beta means omega alpha and omega beta are the intermediate excitons. Or should I put labels on the diagram to show that? So if we were to, if we had infinite or if we had the computational resources, we'd be evaluating this expression on omega gamma. Now it's on evaluated on omega alpha, which is some total. Which is also not true because we don't change this for each omega alpha. Right? This is not.
I don't know, I'm lost. Okay, Dan, let's go to the next slide.
This omega alpha should have, this omega should not be omega alpha, it should be this omega with maybe a line above. I'm getting reimbursed for my trip, that's why I'm laughing. Otherwise I'll be crying. Andre is crying.
So we are finishing meeting in 10 minutes.
Yeah,
Now you need to squeeze your.
You really need to get a move.
So
one
slides.
Okay. So another another process that we looked at is singlet fission, which is known to be a process that one needs to include when modeling MEG, and especially in carbon nanotubes, where it's been shown that singlet fission process cannot be neglected. So when we have a high energy excitation, this singlet exciton, which is always in the singlet state, can decay into two singlet excitons, or it can decay into a state of two triplet excitons that are overall in the singlet state. When considering this process, only one of the Feynman diagrams that we showed earlier survives, and it's this one. Is what we refer to as the exchange channel. and the expressions look similar, only now we work with triplet um, exciton energy and triplet exciton wave function, which we obtain by solving the Bethe-Salpeter equation for the triplet excitons. So these are relatively smaller calculations because there are diagrams that are not included. So these are our results for the MEG rates in our three systems. So by looking at the density of states, you can see that the bi-exciton density of states are redshifted, which is to be expected as the triplet exciton triplet excitons lie in lower energies. And on the right-hand side are all the diagrams for the MEG rates, including singlet to triplet decays, which are the blue lines, and we find that there are a significant contribution to the MEG channel. Note here that the blue lines might be a little exaggerated because of a simplified treatment of screening when solving Bethe-Salpeter equation, which is the term which is the only term that survives when we do Bethe-Salpeter for triplet excitons. So we then calculated the effect of doping the carbon nanotube with the chlorine atom attached to it, and we see that the singlet to triplet rate in the system is enhanced even more. So we concluded that functionalization with chlorine in carbon nanotubes has a significant effect on at least the singlet fission relaxation chain. So in our calculations for MEG, we treat the final exciton state as the final bi-exciton state as a pair of two non-interacting excitons. We want to go beyond that approximation, which is an approximation that has been made in literature so far as we're concerned. And why this is important is because exciton-exciton interactions are expected to have dipole-dipole behavior, or if they're attractive, then we will end up with a lower threshold for MEG, which would be favorable for creating extra charge carriers, as we have a lower bi-exciton gap. So with our methods, we can systematically include all the interactions necessary in order to study exciton-exciton interactions, which are electron-hole interactions, electron-electron, and hole-hole interactions. So these are our diagrams, and we're looking at the intermediate exciton state between exciton alpha and exciton beta. And in order to include the interactions between those excitons, the standard many-body perturbation theory method is to include all the proper self-energy insertions to the non-interacting, now bi-exciton propagator. once all those insertions have been calculated and taken into account into the Green's function, one ends up with the self-energy correction to the non-interacting propagator, which without this treatment would just be the sum of the energies of the two excitons. So we start with adding the Coulomb interaction between the two excitons. So what is, for example, the simplest Feynman diagram that we can come up with? We decouple the excitons into electron-hole pairs, and we add the Coulomb interaction between them. So this is one diagram that arises from including the Coulomb interaction to first order. We find three more distinct diagrams that need to be included. So those are all contributions to the interaction to first order. The expressions look something like this. One ends up with this Coulomb interactions between Kohn-Sham orbitals I, J, K, and L, and these theta functions tell you whether you're dealing with a particle or a whole. So this is this equation includes all interactions between electron holes, which are attractive, electrons, and hole holes. And that's why this method is so powerful in dealing with these type of interactions. Because everything is included. Sorry, I should have shown that before then. But one can go beyond the Coulomb interaction to first order and include excitonic effects into the diagrams that correspond to attractive electron-hole interactions. One ends up with an expression like this, where now all the interactions are taken into account into the exciton wave functions.
So time goes negative now. You're over the limit.
Okay.
And if someone has
Thank you.
plans for the evening, it's
Okay.
everything after this minute is optional. Everyone wants to do this.
Yeah, if somebody has a reservation.
No.
we have to-
I have a. We're done.
No,
Go-
yours conclusions, like keep going.
Show us conclusions. Don't leave without conclusions. If something terrible happens, skip to the conclusions.
Okay, so there are contributions to the repulsive electron-electron hole interactions. Those will be explained. This is our results.
Dan, I'm sorry, isn't the major point of your activities that those can be resummed? Why are you not emphasizing that?
There's the resummation of the.
Well, why am I not hearing the word?
I just went over it.
I didn't realize that that was a big deal personally. It was just kind of another equation that showed up, and it's like, okay.
Well, it is.
Well,
Okay, time is negative, Dan, so just when it matters, remember to emphasize it.
right. So we, these are the results for our bi-exciton energies in terms of density of states. These are our plots. A major concern here is whether our bi-exciton binding energies are so low because we neglect um, repulsive terms beyond the first order in the Coulomb interaction. So we perform the calculation where we treat all interactions on the same footing. In other words, the first order in Coulomb. And we see that bi-exciton binding energies are still sorry, we see that self-energy corrections are still negative. So the exciton-exciton interactions are overall attractive. Or the attractive terms are larger. So experimental results have been performed and reported in literature for a 9-7 single wall carbon nanotubes, which is in the same 2n plus m family as the 10,5 carbon nanotube that we look at, and the reported energy is quite a bit higher than what we see.
Just say of the same order of magnitude.
But it's the same order of magnitude. So slightly what we can do to obtain more accurate results from a quantitative point of view is include include excitonic effects, and to the second intermediate particle fold pair, which is now
Dan, you
already
really need
treated
to
as
show
intermediate.
picture. You're losing even me, and you know.
Consider and what we suspect to be the major contribution to the bi-exciton self-energy is neglecting triplet state excitons, which is also in our future work. But we also need GW and full dynamical treatment of screening, which can also be improved. We've used density function theory and many-body perturbation theory to include excitonic effects in our MEG rates calculations. We've been able to study MEG in several systems. We find that MEG within the solar range is present in those systems, and it's very much dependent on chirality. We studied singlet fission, and we've shown that it's a significant contribution to the MEG relaxation channel in those systems. And it's also enhanced by surface functionalization. We looked at the exciton-exciton interactions, and we've shown that they're likely to lower MEG. But we need higher precision in our calculations, which at this point would come from full dynamical screening and full use of the GW approximation. Thank you very much. I have a different.
I know it's too late and everything. I mean, you have 3 published papers. One of them is a letter. It's rather odd that you would not mention the results presented in that letter in your job talk.
I had it in there.
The what?
It was slightly too. I had it in there. It was slightly too long.
Yeah, slightly.
I have a,
Hey Dan, it's
Practice with stopwatch.
I,
It's critically needed.
I have a different, well, it's not different, it's,
do you
I
do you have
prepared
those
my talk
results
for
at
a
least
more-
in backup slides? I mean, do you have those slides? If somebody, oh, you know, I looked at your CV, it seems you have a ladder, so what's with that? Did you do any work there?
yes, we
you
did,
see.
we used the Boltzmann transport equation to calculate time evolution of occupation numbers.
Well, it's too late to say it now, everybody wants to go home.
But
And then, in the time that remains, think. I have a bunch of comments, I'll send them to you.
You're reading them?
Privately, yes.
Well, let's thank Diane once again.
thank you very much.
For the interview.
Is it
Yeah.
tomorrow? You flying tomorrow?
I'll find tomorrow.
But you're presenting on Thursday.
Yes,
So you have tomorrow for practicing with stopwatch.
yes. And the talk I have for more, I got thrown off by trying to explain things to a different type of audience. I'm plan to be much more technical and avoid a lot of explanations to
Well, I
audience.
believe I forwarded to you the request from your host, Dr. Karasov, that he wanted some generalities in there. I mean, include this, you know, test tubes with different colors of, what's his name, of quantum dots with different sizes. It's kind of the basic thing that everybody who speaks about nanomaterials should show, the structure-property relationship.
Okay.
I'll send you the slide. I will send you even the picture. But then
Yeah,
you're
I
killing me.
would advise it.
I would also suggest somewhere in the beginning, maybe since you talk about multi-carrier over carrier multiplication, MG, whatever you call it, right? Maybe schematically represented. The scheme. And when you talk about the single fission, it's also, you can show somewhere in the beginning that this is your main focus, right? You kind of mentioned it when I came, you were talking about imaging something. So instead of just having the words, show the illustration, people will immediately understand what you are talking about, and you're not spending a lot of time on explanation of these processes, right? And like, MEG